Okay, November 2024, paper 4, variant 1. Question 1, the spring is suspended from a clamp. Figure 1.1 shows a pointer attached to the lower end of the spring. We have this pointer. Student suspends the load of different weights from the spring and records the readings on the meter ruler. We have the reading from the meter ruler and the weight. Using figure 1.2, determine the reading on the meter ruler when no weight is attached to the spring. When no weight is attached to the spring, so when the weight is 0, it would be here exactly. So the length is 43 centimeters. Length is 43 centimeters. It's between 42 and 44. So this is 43. When a weight of 5.6 newtons is added, so 5.6, where is 5.6? So this is 5.5, 5.6, and then we can draw a line. 5.6 would be exactly at this point. Again, it's between 62 and 64. It's between 62 and 64, so it is as well 63 centimeters. 63 centimeters. Okay? Now, can I find the extension when the weight is 5.6? Yes, I can find the extension. Extension equals extended length minus original length. So basically 63 minus 43, which is 20 centimeters. Okay, this is the extension. Using the values, can I find the spring constant? Yes, I can find the spring constant. K equals F over X. F is 5.6 and the X is 20. 5.6 divided by 20 is what? Divided by 20 is 0.28. 0.28. Do not forget the unit. What is the unit of the spring constant? Force divided by extension, so newtons per centimeters. If the extension was in meters or millimeters, the unit would have been newtons per millimeters or newtons per meters. Moving on to C, an object of mass 0.50 kilograms is attached to the spring. Can I find the weight of the object? Yes, I can find the weight. Weight equals mg. So the mass is 0.5 and g is 9.8, giving you a weight of 4.9 newtons. Okay, 1 mark. The object is pulled downwards. The object is pulled downwards and until the tension in the spring is 6.5 newtons. The object is released. Can I find the acceleration? Okay, that's easy. Acceleration equals what? Force equals mass times acceleration. Force equals mass times acceleration, and acceleration is equal to the force over the mass. What is the force? Is the force 6.5? A lot of you might say, well, yeah, the force is 6.5, but to be honest, no, it's not 6.5. How can I find the resultant force? Now, you need to think of the setup. You have the spring. You have the spring. Attached to it is this mass. Okay. There is an upward force. There's an upward force. Upward tension. You said the tension in the spring is 6.5 newtons. So the tension in the spring is 6.5 newtons. But there is another downward force. There is another downward force. What is the other downward force? The weight, which is 4.9, which is 4.9 newtons. So first of all, you need to find the resultant force. The resultant force, F, would be equal to 6.5 minus 4.9, which is 1.6 newtons. This is the resultant force. Then you have the mass, which is acceleration equals force over mass, so 1.6 divided by the mass, which was 0.5. 1.6 divided by 0.5, giving you an acceleration of 3.2 meters per second squared. Meters per second squared. Okay. Moving on. Question 2. We have a drag car. It's a racing car, okay, rocket engine. Anyway, we have the drag car of a mass 1,400 kilograms, and this is the speed time graph of the car showing the speed increasing and then decreasing. The car reaches a maximum speed of 130 meters per second at a time of 6.5 seconds. At the time of 6.5 seconds, at this point, it reached the maximum speed which was 130 meters per second. Okay. Can I find the maximum momentum of the car? Yes. Momentum equals what? mv. Momentum P equals mv. Have the mass, which was 1,400 kilograms. 1,400 times the velocity, which is 130. What's 1,400 times 130 times 130? This is 182,000. You can say 1.82 times 10 to the power of 5. Do not forget the unit. Kilograms dot meters per second, or newtons dot second. This is the maximum momentum of the car. And then state the feature that represents the distance traveled by the car. The feature in this graph, the feature in the speed time graph that represents the distance is what? The area under the graph. Area under the graph. Okay? The graph. Determine the distance traveled by the car in the first 6.5 seconds. Area under the graph in the first 6.5 seconds. This is a triangle. Half times base times height. Half times 6.5 times 130. You do not need to convert anything. So basically, half times base times height. Half times 6.5 times 130, which is what? 0.5 times 6.5 times 130. 422.5. You can say 423 meters. Okay, 423 meters. The parachute opens at 6.5 seconds. The car decelerates. Describe how figure 2.2 shows that after 6.5 seconds the car decelerates. How does the figure show that the car is decelerating? Let's take a look. How do I know that the car is decelerating? Because you have a negative slope. I don't care now. This question is not asking whether the acceleration is increasing or decreasing or what's happening to the acceleration. He's asking if the car is decelerating or not. Yes, it is decelerating after 6.5 seconds. Why? Because there is a negative slope. Okay? Because there is a negative slope. The car or the deceleration of the car is not constant. Deceleration of the car is not constant. Why isn't the deceleration of the car constant? Because there is a curve. For this question, you'd say the slope is not constant, or it is curving, or whatever. Okay, there is a curve. Okay. Describe the energy transfer that takes place as the car slows down. Okay, this is easy. Initially, what was the energy stored in the car as it was moving? Kinetic. And then as it brakes, what happens? The kinetic is transferred to thermal energy. So basically, kinetic energy to thermal or heat energy. Thermal heat, thermal energy. Okay. Now, define the moment of a force and describe the effect that it measures. What is the moment of the force? Basically, the moment of the force is the force times the perpendicular distance. What does it measure? It measures the turning effect. Okay, so basically it is the force times the perpendicular distance. Perpendicular, okay, distance to the pivot. It measures what? Measures the turning effect of the force. Okay, turning effect of the force. A large rectangular block of stone has a square base outside 3.4 meters. Okay, figure 3.1 shows the block at rest. Explain what is meant by the center of gravity. Center of gravity is the point at which all of the weight is considered to act. Okay, point at which all of the weight is considered to act. The weight of the block is 1.3 times 10 to the power of 7 newtons. Calculate the moment of the weight about corner x. Moment equals force times perpendicular distance. Moment of the weight. So basically you want the weight, which is 1.3 times 10 to the power of 7 times perpendicular distance to the pivot. Perpendicular distance between the center of gravity to the pivot. Is it 3.4? Is it 3.4? No, it's not. It is not 3.4. This distance is half the distance, is half 3.4 actually. This distance, this very small perpendicular distance is not 3.4, it is half 3.4, which is 1.7. Okay, so you need to divide by 2. You have to say that this distance is 3.4, but actually divided by 2. So times 1.7. What's 1.3 times 10 to the power of 7 times 1.7? A huge number, which is 22 million. 22 million, or you can say 2.2 times 10 to the power of 7 moments, so it's newtons dot meter. 2.2 times 10 to the power of 7 newtons dot meter. Yeah, no problem. State two different conditions that apply when an object is in equilibrium. What are the conditions that need to be satisfied? What are the conditions that need to be satisfied? No resultant force and no resultant moment. Zero resultant force and zero resultant moment. Okay. Describe an experiment to determine the specific heat capacity of aluminum. You may draw a diagram. We don't need to draw the diagram. But how can I find the specific heat capacity of aluminum? What is the specific heat capacity? C. Or we know that E equals mc delta T. How can I find C? C would be equal to E over m delta T. I need to think about several things. First of all, I need to think about how can I find the mass? Well, the mass using the balance. So using a balance, find the mass m of the block. Okay, first point. Second point, how can I find the energy supplied? Delta T, we will use a thermometer now, but how can I find the energy supplied to a block of aluminum? Well, to heat it up, I need some sort of heater. To heat it up, I need a heater. And this heater would have a certain power, right? So to find the energy from the power, what do I say? Energy equals what? Power times time over m delta t, right? So power times time. To find the energy supplied, to find the energy, to find the energy, what should I do? You have to use multiply the power of the heater, okay? Power of the heater by the time taken, in seconds. This is to find the energy supplied. And then to find the delta temperature or the change in temperature, calculate, find the initial and final temperatures of the block, okay, using a thermometer. And then you've written down, you have to write down the equation. C equals E over m delta T. You have to write it down. I've written it down in this space. You can write it down on the dotted lines if you'd like. Okay, now, an aluminum dish is initially at room temperature. Boiling water is poured into the aluminum dish as shown. Okay. Explain why after a short time the dish and water are the same temperature. After a short time they both have the same temperature. Why is that so? Well, initially the temperature of the aluminum dish is at room temperature, 20 something. Boiling water is at 100 degrees Celsius. So what happens to the water and what happens to the dish? What happens to the temperature of the water? Does it increase or decrease? Temperature of the water, it decreases. What about the temperature of the dish? It increases. You have to say, you have to state that. You have to say that the temperature of the water, yes, okay. The temperature of the water decreases, and the temperature of the dish increases. So this is 1 point. He's saying that initially they become the same temperature. They become the same temperature. So we need to say like that they will eventually reach equilibrium. They will reach equilibrium. Why? Because the energy will be transferred using what? Using conduction. Right? The energy will be transferred by conduction from the energy will be transferred by conduction from the water with higher energy, water with higher energy, to the dish with lower energy, to the dish, okay, with lower energy. Good. Okay. Explain in terms of its particles why the aluminum expands as the boiling water is poured into the dish. Does it expand that much? No, but it does expand. Yes, thermal expansion. What happens during thermal expansion? During thermal expansion, do the molecules themselves get bigger? Does the volume of each molecule increase? No. The volume of the molecules themselves do not increase. What happens is that the molecules themselves get further apart as they gain kinetic energy. Molecules get further apart as they, let's write it down. So molecules move further apart as they gain what? Kinetic energy. The water in the dish evaporates. Explain in terms of water molecules what is meant by evaporation. Okay, this is easy. The most energetic molecules, most energetic molecules escape from the surface. You have to say that the most energetic molecules escape from the surface. Okay, you can say leaving behind the least energetic molecules, but that's a question when he asks why does the temperature of the liquid decrease? If he asks why is there a cooling effect or whatnot. A loudspeaker produces a sound wave in air. The distance between the center of a compression and the center of the neighboring refraction is 0.1 meters. Calculate the wavelength. Can I find the wavelength? Yes, the wavelength would be. Is it 0.1? Is it 0.1? No, it's not 0.1. It has to be 0.2. Why did I multiply by 2? Why did I multiply by 2? Because this is the distance between a compression and a rarefaction. It has to be the distance between two compressions, two successive compressions, or two successive rarefactions. State the typical value for the speed of sound in air. Speed of sound in air would be in the range of 330, maybe 340 meters per second. This is a typical value for the speed of sound in air. 330 would be okay, 335, 40, 45, I guess up to 50. Calculate the frequency of the sound from the loudspeaker. Okay, so you have the wavelength and you have the speed. Basically, frequency equals what? Speed over wavelength, which is 340 over the wavelength is 0.2. What's 340 divided by 0.2 1700 hertz? 1700 hertz. Explain whether this sound is audible to a human with normal hearing or not. Can we listen? Can we hear the sound? Can we hear the sound? Definitely we can hear the sound. Yes, it is audible. Okay. Yes, audible. Why is it audible? Because humans can hear sounds, okay, with frequencies from what? From 20 hertz up to 20,000 hertz. Frequencies from 20 hertz to 20,000 hertz. Yes, this is the normal range for humans. Another loudspeaker produces a sound of wavelength 0.4 meters. Sound from the loudspeaker reaches the sound absorbing surface with a gap of 0.8 meters at the center. Explain whether it is possible to detect from the loudspeaker at either point J or at point K. Can the sound be heard at J or at K or not? First of all, we need to understand what's happening in this question. You have a sound, okay, wavelength, okay, that's passing through this gap, so diffraction will happen. If the wavelength is 0.4 and the gap is 0.8, what what type of diffraction is this? Or in other words, is this a wide gap or is it a narrow gap? Is this a wide gap or is it a narrow gap? 0.4 to 0.8, this would be considered a wide gap. Actually, it would be considered to be a wide gap, meaning meaning that the waves that will pass through the gap will not diffract that much. If the waves pass through the gap now, they will be straight waves. Okay, they will be straight waves, just bending a little at the end. Right, they will bend a little at the end. Now, these waves will pass, they will move in a straight line. Will they bend? That's the question now. Will they bend that much and be heard at J? I think not. Why? Because they wouldn't be able to bend. If the gap was much smaller, okay, if the gap was much smaller, then the waves would have bent much more, okay, they would have spread much more, and they would have been heard at J. That's the whole point of diffraction. Will they be heard at K? Yes, they will be heard at K. Why? Because they'll keep on moving this way and they will be heard at K. So at J, can I hear? Okay, can I hear the sound at J? No, probably not. Okay, why? Because this is a wide gap, and you'd say that not enough diffraction. Okay, not enough diffraction. Okay, diffraction wouldn't reach J. Wouldn't, or you can say yes, small diffraction. It would not reach J. Would it reach K though? Yes, it would reach K. Okay, it would reach K. Yes. Okay, it wouldn't need to diffract. Okay, it would pass right through, passes right through K. Okay, so the whole point, he's actually asking about J. He's not asking that much about K. He's asking about J. Will it reach J? No, because of the diffraction, because that the diffraction is too little, very small diffraction. Why? Because this is a wide gap. This is a wide gap. Okay, a potential divider is made by connecting a light-dependent resistor and a thermistor in series. Figure 6.1 shows the potential divider, a voltmeter, and a direct current. Okay, the voltmeter measures the potential difference across the LDR, which is quite obvious. Define potential difference. What is the potential difference? Again, potential difference or EMF, we have to talk about the work done or the electrical work done. If I'm talking about the potential difference, then I'm talking about the work done or the electrical work done of Of what? I'm talking about the electric work done of the charge while passing through the component. Okay, while passing through the component. We have to say that it is the electrical work done of the charge while passing while passing through a component. Okay, good. Now, the electromotive force is E. The battery, the voltage of the battery is E. Describe how the potential difference across the thermistor can be determined using the reading on the voltmeter. I need the voltage of the thermistor, not the voltage of the LDR. The voltage of the thermistor. Can I find the voltage of the thermistor? Yes, I can find the voltage of the thermistor. If the voltage is E, if the total if the total EMF of the battery is E, and the voltage or the potential difference on the voltmeter is given, can I find the potential difference of the thermistor? Yes, by subtraction. All I need to do is E, okay, basically you need to say E minus the reading on the, okay, on the voltmeter. That's all you do. E minus the voltage on the, or the reading on the voltmeter. Good. Okay, not bad. The resistance of the LDR. Okay, do I have to say the reading? No, we don't have to say the reading. The resistance of the LDR decreases and the resistance on the thermistor increases. Let's write it down. Resistor LDR decreases and thermistor increases. Resistor on the LDR decreases and the resistor on the thermistor increases. This is an LDR and this is a thermistor. What happens, or why would that happen? That's the question. Why would that happen? What are the changes that happen that causes the resistance of the LDR to decrease? This is an LDR, it's a light dependent resistor, so therefore the light intensity should it decrease or increase? The light intensity should increase because they're inversely proportional. Should increase because they are inversely proportional. Okay, the resistance on the thermistor increases. Thermistor depends on the temperature. Again, inversely proportional. So if the resistance increases, this means that the temperature decreases, right? Temperature decreases. Yes, excellent. Explain what happens to the reading on the voltmeter. Explain what happens to when the intensity or the light intensity increases and the temperature decreases. Let's talk about the voltmeter. Now, the resistance decreases, resistance of the LDR decreases. Therefore, the resistance of the voltage or the reading on the voltmeter has to also what has to decrease. So the voltage here decreases. We need to talk about some very familiar things. What should we say? We need to talk about how the resistance, okay, is kind of directly proportional to the voltage. The resistance is directly proportional to the voltage. So we need to say as the resistance of the as resistance of as the resistance of the LDR, isn't it? Yes, the LDR decreases, voltage decreases, and we need to say that the resistance and as the resistance, okay, of the thermistor increases, the voltage increases. We can say that they are directly proportional, and we need to say that the total voltage of the battery, total voltage of the whole circuit is constant. That's why when one of them increases, the other decreases. Total voltage, okay, of the circuit, or the total EMF of the circuit, if you want to say, is constant. So for example, if the total voltage, total EMF was 12 volts, if one of them is 6, the other is 6. If one of them is 2, then the other has to be 10 because you have to add them up and have total voltage of 12. Okay, a solid bar is inside a copper solenoid. Figure 7.1 shows that the copper solenoid is connected in series with the battery and a variable resistor. Suggests a suitable material for the bar. Definitely iron or soft iron. The right hand end of the bar is the south pole. Okay, as shown below. Figure 7.2 shows the bar viewed from above. On figure 7.2, draw at least 6 field lines. Okay, that's easy. 6 field lines. You have south pole and then you have the north pole. Can I draw 6 field lines? Yes, I can draw them. From the north pole to the south pole. Okay, I can draw 3 above and 3 below. Do not forget, please do not forget to draw the direction, the arrows moving from the north pole to the south pole. Okay, from the north pole to the south pole. Yeah. And then I'll draw 2 lines close to each other, indicating that at this point, the magnetic field was stronger. And then the third line, I'll draw it a bit further away, indicating that the magnetic field is getting weaker as you move away from the magnet. So now we have 6 field lines. If you want to draw more, you can go ahead. You can go ahead and draw some lines into the South Pole, for example. Okay, into the South Pole, and some of them moving outside of the North Pole, which is okay. He said at least 6. Yes. The resistance of the variable resistor increases. Variable resistor increases. Explain what happens to a magnetic field surrounding the bar and state how the pattern of the field lines that represent the field changes. Let's take a look again at our circuit. This is the variable resistor. As the resistance increases, what happens what happens to current inside the circuit? What happens to the uh, uh, what happens to the current in the circuit? The current will decrease. The current will decrease, right? Current will decrease. And the current is what defines or what gives you a representation or the strength of the magnetic field, right? So if the current decreases, so you'll have to say that the magnetic field decreases. Magnetic field decreases. And then if the magnetic field decreases, therefore you'd have the lines. Remember when I told you about the lines, the distances between these lines. If the magnetic field decreases, then the lines will get further apart. Lines will get further apart. So you have to say that the current, okay, decreases, therefore the magnetic field, okay, the magnetic field strength decreases, okay, decreases, and the field lines, okay, lines get further apart. Okay, that's all you need to say. Now, you have a square coil. Do I care what is a square coil? No, I do not care. It's a coil just near the other magnet. Many turns, and it's placed right next to the bar. Okay, what happens is that the resistance of the variable resistor is alternately increased and decreased. So we keep on increasing and decreasing the resistance, therefore the current will keep on decreasing and increasing, right? Current will keep on decreasing and increasing. What's happening? What's happening to the current? Is it now a direct current? Or is the current sort of increasing and decreasing, therefore creating an alternating current? Right? It's creating an alternating, or the current is changing anyway, even though if it's not 100% alternating. I know some of you might say, well, the current is not moving the opposite direction. Should I say it's alternating? No, you can say it's just changing. Okay, yes, it's not alternating. It's not alternating, but it's changing. So as you change the current, what happens to a magnetic field? The whole point is what's happening to the magnetic field. If the magnetic field was constant, if the magnetic field is constant, then you won't be able to produce an induced current or an induced EMF in the other coil. The whole point of this question is this is actually a transformer. If you would say, how is this a transformer? You have two coils. You have two coils. You can consider the copper solenoid to be the primary coil and the square coil to be the secondary coil. Therefore, as you increase and decrease the current, you're increasing and decreasing the magnetic field. And when you change the magnetic field, you keep on inducing a current. That's all we'll say. That's all we will say. So as the variable resistor increases and decreases, the current, okay, changes. Current changes, increases and decreases, creating, okay, changing and thus changing the magnetic field. As the magnetic field keeps on changing, it cutting, right? Keeps on cutting the square coil, producing an induced, okay, producing an induced EMF and current in the coil, in the square coil. Okay. Now, question 8. The nuclide notation for the radioactive isotope carbon is 14 and 6. Use the symbols. Can I draw an atom? This is a chemistry question. 3 marks just to draw some symbols. Okay, that's easy. How many protons do I have? I have 6 protons. How many neutrons do I have? 14 minus 6, so I have 8 neutrons, 6 protons, and how many electrons? I have 6 electrons. So let's draw. Okay, let's keep on. Let's draw. I have 1 neutron, 1 proton. So I have one of these. Okay, another neutron and another proton. Okay, another neutron and another proton. Okay, another proton. So now we have 4 protons and only 3 neutrons. Okay, 5 protons now. 5 protons and 5 neutrons. Okay, 6 protons and 6 neutrons. We need to add 2 more neutrons, and that is it. So this is the nucleus, right? This is the nucleus. And then how many electrons do we have? We have 6 electrons. We need to just draw the 6 electrons. Do I have to draw them as 2 and then 4 or whatever? No, I do not care about the shells. You can just draw 6 neutrons in the electron shell, and that would be it. Okay, that would be it. Okay, that's it's quite easy, right? Now, describe how the composition of a neutral atom of carbon is different from the composition of a neutral atom of nitrogen. It's quite easy. How many protons and neutrons are there in carbon, and how many protons and neutrons are there in nitrogen? We might say that the nitrogen, okay, has 1 more proton, right? Has 1 more proton and 1 less neutron. That's all you need to say. 1 more proton and 1 less neutron than carbon. Okay? They have the same mass number, yes, but it has 1 more neutron or 1 more proton, I'm sorry, and 1 less neutron. Now, carbon 14 decays by beta emission. What state the name of a particle that is identical to a beta particle? It is an electron. Electron is identical to a beta particle. Describe the change that takes place in the carbon-14 as a beta particle is emitted. How do we emit beta particles? Basically, a neutron is split. We have a neutron inside the nucleus, which is split into a proton and a beta particle. Okay. Neutron is split into a positive and okay. The half-life of carbon is 5,700 years. A very old object contains 1.2 times 10 to the power of 11 atoms. When it was manufactured, it contained 9.6 times 10 to the power of 11 atoms of carbon-14. Determine the time that has passed since it was manufactured. Initially, it was 9.6. How did it reach 1.2? 9.6 times 10 to the power of 11. How did it reach 1.2? By division. You keep on dividing by 2. So when you divide by 2 first, it's 4.8 times 10 to the power of 11. You have not reached 1.2 yet. So divide by 2 again. 2.4 times 10 to the power of 11. Divide by 2 again. 1.2 times 10 to the power of 11. Which means that you have taken 3 half lives. 3 half-lives. 1 half-life is how many years? It's 5,700 years. So 3 times 5,700, 3 times 5,700 is 17,100 years. So it's 17,100 years old. Right? Okay. Now, question 9. The Milky Way is a galaxy in which the solar system is located. State what a galaxy is. What is a galaxy? It's a cluster of billions and billions of stars, right? Contains billions of stars. Of billions of stars. The Milky Way has a diameter of approximately 100,000 light years. Determine the distance in kilometers. We know that 1 light year is what? 1 light year is 9.5 times 10 to the power of 15 meters. If you have not memorized the number, it's okay. You can work it out by saying that the distance is equal to the speed times time. You can do it. Distance equals speed times time. Speed of light 3 times 10 to the power of 8, and the time taken 365 days, 24 hours, 60 minutes, and 60 seconds. You will get a number of 9.5 times 10 to the power of 15 meters. Okay. In kilometers, this would be, if you divide by 1,000, this is 9.5 times 10 to the power of 12 kilometers. This is for 1 light year. 1 light year. The Milky Way is 100,000 light years. So basically, you need to multiply by 100,000. It would be a huge number. Yes, a huge number. So it's 9.5 times 10 to the power of 17. You add 5 zeros. 10 to the power of 17 kilometers. Definitely a huge number. Astronomers determine the speed and the distance from the Earth of a far galaxy that is moving away from the Earth. State one observation that allows the speed, okay, at which a galaxy is moving away to be determined. How can we determine the speed? Again, there's a difference. How can we determine the speed? By the redshift. The speed is using the redshift, which is the change in the wavelength or the increase in the wavelength. But how can I find the distance of this galaxy? Okay, finding the speed using the redshift. Finding the distance is by the brightness of the supernova. Okay, by the brightness of the supernova. Okay, have two very important values. If you want to find the speed, it's using the redshift. If you want to find the distance, okay, using the brightness of the supernova. State how the speeds of the galaxies and their distances are related. The further away, the faster it is, right? The further away a galaxy is, the faster it is. Therefore, they are directly proportional. Okay, speed and distance are directly proportional. Why? Because you have the equation. H naught equals V over D, Hubble's constant. The best estimate for the Hubble constant is 2.2 times 10 to the negative 18 per second. Use this value to calculate an estimate for the age of the universe. Can I find the age of the universe? Yes, the age of the universe is 1 over the Hubble's constant, which is 1 over 2.2 times 10 to the negative 18. He wants to find the time in seconds, so you will not convert anything. Just 1 over 2.2 times 10 to the negative 18, which is 4.5 times 10 to the power of 17. Seconds. Power of 17. What? Seconds. This is the age. If you want to find the time in years, okay, it would be around 13.8 or 14 billion years. Okay.